Swayam Prabha. Digital India. Educated India.
We were discussing about the chemical shifts and this is just a quick recap on what we did last time. So, we have a nucleus which is here and you have an electron cloud around it which is indicated by the green dots here, and we have an applied magnetic field which is B0 indicated here as B0. In the previous class I might have said it as H0, but it does not matter, it is B0 here. And this B0 field induces a current in this electronic cloud and which produces a magnetic field which opposes the externally applied magnetic field, and therefore the field seen by the nucleus is Bi, and that is given by B naught into 1 minus sigma I. So, that is the sigma I is the so called screening constant, and this can vary depending upon the environment of your molecule. And the precessional frequency of a particular nucleus will then be nu omega I, or this is if you put it in terms of frequency in hertz, that is minus gamma Bi divided by 2 pi, and Bi is the field which is given here. Now this will then depend upon the magnetic field strength. Therefore, since we want to characterize only the screening or the electronic environment around a nucleus, we define an entity which is given here, delta I is equal to nu I minus nu R divided by nu naught. Nu R is a kind of a reference compound and you measure the absorption frequencies with respect to a particular line of a reference compound, and then this will be a very small number compared to nu naught. Nu naught is your spectrometer frequency, this corresponds to B naught. So, divided by this nu naught, then of course this will be a number which will be very small, and you multiply therefore by 10 to the power 6, although that is not, I wrote it in the previous one, and that is called as the ppm. Delta I is expressed in terms of ppm. Higher delta I means higher Bi, implicating downfield shift, and therefore it is less screening, and you will have a spectrum which is at a lower higher frequency of absorption. And higher sigma I, lower delta implies that greater shielding, that will mean in upfield shift and vice versa. So, this is of course we already did this last time, and let me explain that a little bit more here. We take this example, this is vinyl chloride. So, vinyl chloride has 3 protons. This has 3 protons here, this is let us label them as H, A, Hb and Hc, there is a double bond here, and chlorine is an electron withdrawing group, therefore it changes the electron density in these proton around the protons. So, we said whatever is the electron density, that determines how much will be the screening. So, therefore, if the electron density is lower, then the screening will be less, and therefore that will be at a higher frequency of absorption or the lower delta value, the higher delta value. So, the frequency absorption is going like this. So, the chemical shift here, the Hb, which is the closest to the chloride, which is the with the electron withdrawing group, therefore this will have the lowest electron density here, therefore the energy separation, the Bi will be highest for this particular nucleus, and this nu B therefore will be the highest, because the energy of absorption will be high, the energy separation will be higher. This will be followed by nu A, which is indicated here, this is the trans, and therefore the effect of the chloride will be, after this it will be more at this point, which is trans to the chloride group, and this will have the next frequency which is nu A, and the one which is the cis to it, that will because of the van der Waals interactions and things like that, the screening will be more here, therefore the lowest delta will be for the nu C. Therefore, the frequency increases in this order and the chemical shifts numbers delta values will increase in this order. Okay. So, this is how the chemical shift occurs because of the screening by the electron cloud around it. And clearly this is an important parameter which will describe the electronic environment and therefore the structures of the molecules. And a chemist used a large number of molecules to characterize this chemical shifts and the functions. And what are the reference compounds? I said there is with respect to a reference compound to define the chemical shift. So, for the proton there are several reference compounds which are used. TMS is tetramethylsilane and this is it has one line. So, that is taken as chemical shift, that line is taken as 0.0 ppm. And TMS is one which is used whenever your solvent is chloroform or DMSO and things like that, and it is single line and which is the most upfield because the screening is the highest for that. There are 3 methyl groups and therefore silane SiCH3. So, therefore, this is the 0 ppm CH34. Okay. Now, tetramethylsilyl propionate, this is the molecule which is used for soluble systems. If you are working in water, then typically you use this tetramethylsilane propionate, and that also is one line, and other things are deuterated, and you will have one line, and that is you have 0.0. Another common compound which is used is DSS, sodium 4,4-dimethyl 4-silapentane sulfonate. This has many lines, but if you deuterate all the other protons excepting one, then you will have only one line. Otherwise, you have the most upfield line which is taken as 0.0. Other compounds are also used, acetonitrile is used sometimes, dioxane is used, tertiary butanol is used, and various different kinds of compounds are used for referencing. And what numbers which are given here are with respect to the TSP or the TMS, and you have this one as the reference chemical shift, and others will be a reference according to that. For carbon 13 similarly you use TMS, TSP or DSS, and these are all at 0 frequency. For nitrogen 15 you use ammonium chloride or liquid ammonia, and both are these, their chemical shifts are taken as 0.0, and for phosphorus you use 85% phosphoric acid, and that also the line is taken as 0.0. So, all either you add these things internally inside the sample itself, or you put these in a capillary and insert that in your sample tube, then it is called as an external reference. If you put that inside the molecule itself, then it is called as internal reference. Okay. So, I can write that here. So, you can have an external reference in that case the capillary containing the reference compound is introduced in the sample tube. If you directly put this molecule inside your sample, then it is an internal reference. Sometimes you use if you are working with water, you look at the water signal itself. You look at the water signal itself and make that as the reference compound. Often you do not like to put additional molecules inside your sample, especially you are working with biological systems with proteins or nucleic acids or any other biological system. You do not want to introduce an external molecule, external perturbation, because it can change your conditions, it may change the pH or things like that. So, when you do not want to do that, then what you do is reference your water molecule, water signal with respect to that, and use the water signal itself as a reference compound. That often is done. Now, so having worked with a large number of organic molecules, the chemists have come out with certain kinds of understanding as to what sort of groups will have what kind of ppm in their values. And this actually figure shows that sort of an information here. So 0 ppm is what we said earlier, this is the TMS or TSP or whatever, and if you have saturated compounds and those signals will appear between 1 and 2 ppm. You have the allylic ones, they appear here in this region, and you have the CH2X which are the electron withdrawing groups here, CH2O, CH21 or these ROH alcohol. Now what we are talking about is the signals from R, not the OH, okay, and those ones will appear in this area. Then you have the vinylic compounds, and which I showed you the vinyl chloride earlier, and those ones will appear in this region 5 to 6 ppm. And if you have the aromatic compounds, the aromatic compounds will appear between 6 to 8 ppm or 8.5 ppm. All these benzene rings, various kinds of rings which are there, the protons in those ones will appear in this area. And if you have the aldehyde group, the RCHO, then we are talking about this particular proton here. This proton will appear at this place here, and RCOOH, this is the carboxylic acid group, this proton will appear here. And here of course the OH also will appear in this area. It can vary from here, this is a wide range here, depending upon what the R is, you will have a wide range of things, and depending upon what the conditions are, what is the pH of the solution, you can have this OH proton appearing in a wide range of frequencies. So therefore it is very sensitive to the conditions of your sample, and that proton chemical shifts can vary quite a lot depending upon the environment in your solution. Similar exercise, now let me explain to you, I explained last time about the aromatic ring effects. The aromatic ring effects, what is shown here is, if I have a ring, I showed here a ring and it has the electron cloud above and below, and it produces a external induced magnetic field, because of the currents inside this, the field goes like this and like this, and you can have a proton anywhere present. So depending upon the proton, you will have different kinds of chemical shifts. What are shown here are the iso shielding lines. So let us say I have a ring here, and then I draw a cylinder around this. If I draw a cylinder, the electronic current is here, okay. Now let us say I consider a position, I mean this, I define the coordinate system here, and this coordinate system here, this is called the Z coordinate and this is called as the, these are the cylindrical coordinates. So rho and Z are the cylindrical coordinates. So depending upon where your proton is, suppose I say I have a proton here, okay. So it will have a certain coordinate, Z coordinate and the rho coordinate. So this is the coordinate of these are the cylindrical coordinates for this particular proton. What will be the chemical shift there? So what has been done is the previous slide which I showed here. So what is plotted is the Z versus rho, one particular quarter of this. So this entire circle, instead of the entire circle, you particularly take one quarter of this. So you have this cylinder lying on top here like this. So I take this particular quarter here. So if I plot this, how the Z axis is on this going up the Z axis, on this axis on the right orthogonal is the rho axis, and what are the chemical shifts in those ones. So now you see here, as you go up along the Z axis, so that is if you are on the top here, if you are there, then you have positive shifts here, plus 4.00, 3.0, 2.0, 1.0. In all these positions, at all these positions it will have the same 1.00. If you are here along this contour, then you will have 0.00. If you are here 4.00, if you are here then it is 4.0. So this is all positive numbers here, and this is the 0 axis, this is the no shade here. And if you are on this side, as the rho is increasing here, you start getting negative numbers, which means you are on the horizontal plane of the ring. If you are on the plane of the ring, then you get negative shifts, and that is to be expected because the field is opposing. The field is opposing in the horizontal plane. In the vertical axis, the field is adding to your main H0 field, and therefore there it causes a positive shift, the isoshielding curves, and this is on the negative side. So this is the calculation which has been done by theoretical procedures using the theory of chemical shifts in great detail, and therefore this is extremely valuable to predict depending upon where you are with respect to the ring where you are, you will have different kinds of chemical shifts. This is important to know how far it can go, and these are in certain units of 1.39 angstroms. You see, each one of these, the Z and the rho are given in units of 1.39 angstroms. For some particular reason they have used this number, 1 is the chemical length of a carbon-carbon bond. So, particular bond which they have chosen, and they have given this this is taken from this reference, the Journal of Chemical Physics, you see 1958, quite old, and of course those things are valid all along. So this is an important effect, which is the ring current effect. This is also called the anisotropy, because of the ring there is an anisotropic in the chemical shifts. Depending upon the orientation of the ring, depending upon the location of your proton with respect to the ring, you will have different chemical shifts, and that is drawn in the form of a contour. Okay. So because there are two coordinates which are responsible, one is on the rho and one is z. Depending upon the combination of these, you will have different kinds of shifts. Okay. So this is what explained to you. Now similarly for the that is for the proton, similarly you can also have the carbon chemical shifts. Now the carbon chemical shifts also, you see, this carbon has a much wider range of chemical shifts. While proton went from 0 to 10 or 12 ppm, carbon goes from 0 to 200 and 230 ppm. You see, quite a wide range of chemical shifts you have here. And once again, depending upon the nature of the carbon, you have different kinds of chemical shifts. The highlighted carbon is indicated in red color here. So you have RCOC that appears in this area, C double bond CC that appears here in this range and this range, and C aromatic you have this one here, CSR, NR2, CH saturated alkanes, CBR and CI. So CCI, so all of these are the halides here, iodine, chlorine, fluorine, and those ones will appear in this area. R2C, CH2 is, if you look at this Ca carbon, it will appear here, and if you have the aromatics, the aromatic carbons will appear from 100 to 150 ppm. Heteroaromatics means if you have this heteroatoms substituents over there, they will appear here, and RC triple bond N, that will appear here, sulfoxides, sulfones. See, this is the result of enormous amount of data collection. There is a huge database. Such databases are available in the literature, and there are also many volumes of database of the chemical shifts reported, and from this you draw this sort of a picture. So amides appear here, RCONR2, RCO2 R dash. So these are the acids, esters here, and these are the carboxylic acids, and they appear in this region 150 to 200 ppm. Typically the carbonyl carbons. So you see typically the carbonyl carbons appear in this area, aromatic carbons appear in this area, aliphatic carbons appear in this area, and mostly we will be dealing with these kind of chemical shifts when we do with proteins or nucleic acids, because there you have the aliphatic carbons, they will all appear in this area, and the aromatic carbons, the carbonyl groups in peptide bonds and things like that, they will all appear in this area, aromatic carbons in this area, and so on and so forth. Phenylalanines and all of these aromatic rings in amino acids, they will appear in this area. So this sort of a classification is extremely useful for understanding the structures of molecules. First of all, you have to assign the individual resonances to particular nuclei, both proton and carbon, and once you have done that, then you can go forward to see what sort of a structural indicators they are. And now there is another important parameter which is called as the spin-spin coupling. Now the protons, while they are surrounded by the electrons, and that is of course important to screen the magnetic field, but the protons themselves, they also interact with each other. Suppose I take this CHCl2 and CHO, this proton and this proton, they are separated by 3 bonds. Okay. So let me write here C, let us say CH, okay, this is this molecule, right. So now you have this proton, and here you have Cl. These two protons interact with each other. because they are all they are magnetic moments, they are magnetic dipoles. Therefore, they interact with each other either through directly through space interaction. So, there are two kinds of interactions possible, dipolar interactions, okay, dipolar interaction, or there is other what is called as through the electrons. Through the electrons in the intervening bonds. Now, dipolar interaction is a separate story. This is actually most applicable in the case of solid state NMR and relaxation phenomena, and we will also talk about it a little bit later. And mostly for what we see in organic molecules or small molecules, these are the interaction through the electrons, and this is also called as J coupling. Spin-spin coupling is also, this coupling is called as J coupling. Okay. What is the result of this? I am just showing you the spectrum here. You have the delta B, this is the chemical shift. You have the chemical shift of the particular nucleus, let us say we call this one of them as A, other one as B. So, let me say this is A and this is B, and you have the chemical shift of B here and the chemical shift of A here. But this line is now not appearing at delta B, it is actually getting split into two lines. This is split into two lines too, and the separation between them is the so called spin-spin coupling constant, and that is JAB. Why does this happen? How does this happen? So, we can represent this as in this manner. Let us say I have a proton here, I write a proton here, and this is my H, C, C, H. So, this is the orientation of the spin here. If I call this as, let us say, the alpha state is the alpha oriented parallel to the field. So, there are also electrons here. So, there are also electrons here, right. In the bonds there are electrons. So, these electrons, what happens is the proton nuclear magnetic moment polarizes the electron spin, electron magnetic moment, and makes it orient in a direction opposite to the alpha state or to the proton nuclear orientation. Now, since these two are in the same bond, so this electron which has this bond has two electrons, the second one will be oriented in this manner because they have to be anti-parallel, that contributes to the lowest energy state, and therefore it will be anti-parallel. Once this one is there, then suppose this were carbon 13, suppose this is carbon, this also has a nucleus, and now it will orient this nuclear, I should use a different color here again. So, this is the magnetic nuclear spin, it orients it like this, and this in turn orients the electron here, it will put in this direction, and the pairing electron it puts in this direction. And now once again let us put the carbon will again be up. So, the carbon here will be up if it has to be open. Now, then I put the proton once more, the electron I put it here like this and then like this, and what will happen to this? So, therefore, this will become like that. So, these two protons are anti-parallel to each other. Okay. So, therefore, they are oriented in opposite direction. Now, in terms of the interaction between these two, how do we describe this? We describe this interaction as J I A dot I B. Now, if they are opposite to each other, this interaction will be, it will produce a negative number, right. Ia dot Ib is Ia Ib cosine 180, Iza Izb cosine pi. So, if they are exactly opposite to each other, this will be negative. Therefore, if they are opposite to each other, they will have a different energy level. Okay. So, because of this, now if J is positive, this state will be the lower in energy compared to the other state where this can be positive also. It is not that the other thing is not possible. It is also possible that this fellow will become negative down here, this goes up, the other configuration is also possible. The other configuration will be, you have this here, the other one is, let us say it is also like this is another configuration. Okay, this is configuration 1, this is the configuration 2, this is also possible. This will have a different energy compared to this, and this energy will be lower compared to this. Okay. So, in other words, the proton alpha state will be split into 2 levels. So, now I draw here the alpha state of the proton. This will have 2 energy levels because it will be split into 2 because of the orientation of the other spin. Now, this is, let us say I call it as nu A, and this is alpha state of nu A, and here the I will write here the spin state of the X nucleus. Let me write the X nucleus, and if this is beta, this will be down the energy because these are opposite orientations, and this is alpha here, this is the orientation of the other spin, this is the beta spin, the B spin orientation. So, therefore, these two have different energies. Obviously, instead of one line coming here, there will be 2 lines coming there. If I call this as the beta state, so here again it is split into 2. Okay, it is split into 2. Why? And the beta with the alpha goes down. So, this one, this is the alpha and this is the beta, because I1 dot I2, if the 2 are in the same direction, if the 2 are in the same direction, it will be positive energy. If they are in the opposite direction, then it will be negative energy. So, therefore, the beta alpha goes down, beta beta goes up, alpha alpha goes up, alpha beta goes down. So, therefore, we will have this orientations like this. And what is this energy separation here? This will be of the order of few hertz, and that is J, that is the J which is indicated. Similarly here. Now, what are the transitions possible here? So, the transitions will be dependent on delta m is equal to plus minus 1. So, what instead of this transition, I will have 2 transitions now. Which are the 2 transitions possible? I can have a transition m is equal to, from m is equal to 0 to 1. So, what is the m value for the beta beta? The m value here, let me write the m value, this is minus 1, the beta m value is 0 here because of the beta alpha, one is down, other one is up, the sum of the 2 m values is equal to 0 here. Similarly, this one is 1 and this one is 0, the total m value, okay, the summation of the m values I am writing here of the individual spins. This is now I should have a transition where delta m is equal to plus minus 1, okay, this is summation mi of the 2. Okay. Now, which transitions are possible? I will have a transition possible from here to here, 1 to 0 and 0 to minus 1. I will have another transition possible here. There are 2 transitions possible. Okay. So, therefore, this leads to a separation. Okay. How much is this separation here? This is j by, you can calculate what is the value of that. This will be j by 4, this will be j by 4, the separation will be j by 4, this will also be j by, and then the energy which is going down will be j by 4. Okay, that is j by 2 total. So, now if you look at this, therefore, you will have 2 lines for each one of those. So, we will have 2 sign lines. So, one is between these 2 states, this is from here to here which I indicated, and the other one is from here to here, 0 to minus 1, up and down both are possible. Okay, therefore, delta m is equal to plus minus 1, we will have these 2 states and the separation between them will be j. Okay, this is how the splitting occurs between the 2 energy levels. So, we can do the same thing for the other spin as well, and that is beta spin. I wrote it for the nu A. Notice this is in megahertz, okay, this nu A is in megahertz and this is in hertz. Therefore, this is a very small number, this is a very small number. So, similarly, one can write for the nu B as well. So, I can write for nu B as well. I will also have 2 lines corresponding here, and the separation between them will be, this is nu B and this separation will be JAB. I showed you for the 3 bonds you can have coupling from one bond, you can have one bond coupling, that is let us say proton to C13, or you can have proton to nitrogen 15. You can have 2 bond couplings, this is you can also have 2 bond couplings, that is like CH here. So, that is a coupling between these two, this is a 2 bond coupling. I showed you the 3 bond couplings, that is H, C, C, H, these are 3 bond couplings. The same mechanism applies in all of those cases. And notice here this, how far does it go, how far this relay goes? It does not go beyond 4 bonds, okay, because if you go beyond 4 bonds then the effect will be relatively small, then you do not see the coupling as much. So, typically, so you will see from 1 to 4 bonds coupling, and they have different ranges. So, if I want to write these are typically of the order of 1 bond couplings of the order of carbon couplings are of the order of 140 to 200 hertz, that is and then you have 90 to 100 hertz for the proton, this one, and this is for this one, and the 2 bond couplings are of the order of 14 to 18 hertz, and 3 bond couplings will also be of the order of 3 to 15 hertz. Okay. And incidentally, one more thing one has to notice is the 2 bond couplings can have a negative J value. Now go back to this previous slide here. Now I showed you the value of J, interaction is J I1 dot I2, right. So if J is positive, I1 dot I2, if it is negative, then there is a decrease in energy. If J is negative, then it will be I1 dot I2 negative will be positive, right. So the total will become positive. In the case of 2, just if you take 2 bond, let us say H, C, H, and I draw the spins here like this, and let us say this one is like this one is like this electron spin, and I have here this one let us say like this one like this, and this is the most stable state. Let us assume this is the most stable state. Now you see the 2 proton spins are parallel to each other, and this is, if it is the stable state, this actually has to be, energy has to be negative. So this parallel state has lower energy So, this implies that J is less than 0 because it decreases the energy value, and therefore the geminal couplings, the so called geminal couplings are negative, whereas the vicinal couplings and the one bond couplings, they are all positive. Okay. So, I think I will stop here. Again we go to the next one in the next class.